Good morning, guys. How you doing? I hope everything is going well. We're going to continue the chemical equilibrium lecture now. I'm going to get into the theory of what we're going to be talking about. And like I've said previously, I will do some lecture, we will do some problems, and then there will be an end to this video. We'll go to the next video. There will be more practice for each of these types of problems at the end of class. So this should follow the order of the lectures as you have them. So hopefully that will work for you. And let's go ahead and get started. All right, so let me share my screen. And I'm going to pick up with my slideshow from here so that we can talk about what's going to be in the overall lecture. Now, not all of this will appear in the first part of this. Really, I'm looking to do each of these sections will probably be their own little mini lecture, but it's not always that clearly or nicely cut down. So that's what we're looking at. So we're going to start with the concept of equilibrium and what an equilibrium constant is. We will then talk about writing equilibrium constants. We'll talk about the relationship between kinetics and equilibrium, and we'll define all of that. We'll talk about what the equilibrium constant tells us. We'll talk about the factors that affect chemical equilibrium, and then we'll talk about experiment 1, so the chemical equilibrium lab. I think that's everything for that. There's a separate video for the chemical equilibrium lab too. There's always a video for the lab, and then the material is covered in the lecture, so there's both. All right, let's keep going. If there are any questions, comments, problems about anything so far, please let me know. Again, email, phone, video chat, we can WebEx. That is entirely up to you. Just make sure you let me know. All right, so let's talk about this concept of equilibrium. I have a picture here, and my point in showing you this picture is I want you to think about a couple of things. Can you tell me specifically how many people are in that store at this time? Chances are no. It depends on how big the store is and what the fire code says for how many people can be in there and yada, yada, yada. But based on the length of that line that exists, would you expect that the number of people in that store in 5 minutes would be significantly different? I would guess no. Okay. Will they be the exact same people? Probably not. And what would I call that scenario? Well, so in my head, what I see is that there's a number of people inside and a number of people outside. The number of people inside is fairly constant, but there are people going in and out all the time. And I would typically call that a steady state. We often hear that phrase used, steady state, okay? And this is a fairly common thing for us to see. Now, that doesn't mean that there aren't changes happening. There are changes happening. There are different people in that restaurant now than there will be in 10 minutes. But that does, from a net standpoint, from way up above it, we don't notice any difference. Okay? That's what equilibrium is like. Okay, so that's what I need you to keep that in mind as we continue talking about equilibrium and what it is. Right? Some other things I need you to think about before we get into real definitions are a couple of things that we're going to talk about here. So it's a summer day. We're here in South Carolina. You make iced tea. Pretty common here. Being in the South, you add sugar to your iced tea to the point where there's solid sugar at the bottom of the glass. Fairly common. You sit outside on the porch and drink it slowly, and the next time you look down, the solid sugar's gone. Why? What happened? I want you to think about that. But I'm going to tell you what I think. As I sat there, the temperature of that fluid went up. And as it went up, more of that solid sugar is able to dissolve in that solution. Okay? So there's a temperature dependence that goes on with that thing being dissolved. Okay, another thing you may or may not have done. You're getting ready to make rock candy. So you've probably seen rock candy, sugar crystals that are on a stick, sometimes colored. In order to do this, you dissolve sugar in hot water. All right. Then you let the pan cool down very, very slowly without disturbing. And then you take and shove the stick into it. right? And all of a sudden, these things just crash out of the solution. You get these rocks that form on this stick. What exactly has happened here? Well, there's a couple of things that have happened here. When we did this setup and we raised the temperature on this sugar and we got as much dissolved as we possibly could, that's a saturated solution. So we've got as much dissolved as we can. Then we changed the temperature on that and we let it drop. But none of that solid has crashed out if we leave it undisturbed. That's a situation called supersaturation. What that means is that at that given temperature, there's more dissolved than there should be, which happens when we change temperature. We can do that. And then adding that stick to it, giving it that point of place to precipitate, immediately crashes out what shouldn't be in solution at that temperature. So that's how we do that formation. And that's what we talk about in terms of supersaturated, saturated, the fact that the equilibrium was set for this temperature, but now we're at a different temperature. What has happened in between? All of those things are part of what we're talking about. Okay. I'm an insulin-dependent diabetic. I carry insulin with me all the time. Unfortunately, I'm not so great about taking it out of the car. Sometimes I will leave it in, I have a little purse and a big purse, and I'll leave it in the big purse and leave the big purse in the car, and it stays there a lot longer than I was anticipating, and I come back and I pick up that bottle of insulin, which should be clear, and it's not clear. It's milky. I find solid in the liquid. And the question is, what happened? What happened to that? And if I put that back in the fridge, is it going to change? So I will tell you from experience that putting it back in the fridge does not change it. And of course, I didn't necessarily know what had happened to it, but I have figured that out. One of the things that we find is that if we have insulin that's been heated like this, it works when it's clear, but it doesn't work when it's cloudy. And that's because insulin is a hormone. So it's a big biological molecule that's all tied up, it's contorted in the way it should be due to the intermolecular forces. When we heat it, it denatures. And so those bonds in the intermolecular forces change the shape and the structure of that molecule. That is not a reversible process. Okay? So once it's been undone, you can't redo it. And once it's been undone, that insulin is no longer usable by my body because it's no longer the right format. Okay? It doesn't look right. So it's and I know this is really old school. Well, no, I can give you a better one. It's like trying to shove a USB into a USB-C. They're completely different, I mean, a USB is fairly large, USB-C is fairly small. So it's very difficult to make that work. It just doesn't. And that's what we're talking about there, okay? Now here's another question for you. Are all reactions reversible? What does reversible mean? Well, I just said that the insulin situation is not a reversible reaction. So that implies that there is a reversible reaction that might be able to happen, and that insulin dependence is not one of them. So there are reactions that are reversible, and that means they can run either direction, no matter which way we write it. I can write it as what I would call reactants going to products, or I could turn around and write it as products going to reactants, the way that I initially wrote it. But I could turn around and then make those what were initially products, then the reactants. Both of those reactions should be things that we can do. And that means that it's reversible. Now, not everything is like that, okay? HCl is a strong acid. So if I put HCl into solution, it completely dissolves and it dissociates. So I get H plus and Cl minus from it. When that happens, they do not reassociate to become HCl. If they do, it happens for like 2 seconds. This is not considered a reversible process. And that's why it's a strong acid, because it doesn't go backwards. Okay, so not all reactions are reversible, but most of them are to some degree. And that's a lot about that. That's a lot of what we're going to be talking about with equilibrium. Okay, so hopefully there are no questions about that stuff. Well, let's get into the rest of this. So what does equilibrium mean? All reactions have a point where they are in equilibrium. Equilibrium means that the rate of product formation is the same as the rate of going backwards to reactants. So when I take a measurement on this, no matter what time I take that at, the product concentration does not change. The reactant concentration does not change. So I can do this now, I can do it in 5 minutes, and those concentrations should not change. That's what equilibrium means. So no net change in concentrations are noted. This does not mean that no reactions are happening. Okay, we can label those molecules in ways so that we can track them. And reactions forward and backwards keep going, but we see no net change. And so that means that the rate of the forward reaction, how fast you make product, is the same rate as how fast those products break down to make the reactants again. Okay? Now, not all equilibriums are the same. We talked about HCl being a strong acid, and the fact that it doesn't go backwards. Not all acids are like that, okay? Acetic acid is a weak acid, all right? So when we have acetic acid, it's not completely dissociated. When it comes apart and dissociates into H plus and the anion for the acetate anion, it does go backwards, okay? And there's a fixed ratio that exists at a given temperature. So that's what we're talking about when we talk about that ratio, okay? Some reactants favor reactants over products, some favor products over reactants, and sometimes they're roughly equal. And of course, this depends on which way I wrote that equation, which way, lots of things. So we're going to have to pay a lot more attention to that. So that means that the forward reaction rate equals the reverse reaction, right? That does not mean that there are equal concentrations of the reactant and the product. That's not what that implies. Those concentrations are based on the equilibrium constant. We'll get to that in a few minutes. Concept above is very different than reversible, okay? So when we talk about reversibility, we're talking about the ability of that reaction to go backwards. That doesn't necessarily exist. But that equilibrium, whatever that ratio is supposed to be, it will exist after a finite period of time. So if I put HCl into solution, it will dissolve, it will dissociate, but that reaction is not reversible, but it's still reached an equilibrium. Okay, so they're two different concepts. Not all reactions are reversible, as we mentioned. Okay. Now, equilibrium can be reached from either direction. Now, what I mean by that, I have a reaction, and I'm going to share something else. Move this over. I apologize. I should have set this up this way before.